The global thermostat isn't just creeping up anymore, it's practically sprinting. And that's bringing with it this intensifying drumbeat of extreme weather events.
Yeah, it's really noticeable.
We're talking record-shattering heat waves, buckling roads, unprecedented floods, redrawing coastlines, wildfires painting our skies with ash. It's not just a feeling. The numbers tell a stark story.
Absolutely.
I mean, in 2024, the annually averaged global mean near-surface temperature actually hit 1.55 degrees Celsius above pre-industrial levels.
That's a huge number.
Think about that for a moment. It was the warmest year in 175 years in observations. It's a powerful, undeniable signal of the profound challenge staring us down. Welcome to the deep dive. Today, we're not just scratching the surface. We're trying to cut through the noise, the headlines, all that often overwhelming information to embark on a really crucial exploration. Our mission is to unpack this intricate landscape of future climate technologies. We're synthesizing insights from a pretty comprehensive scientific review.
Yeah, pulling it all together.
We want to help you understand not just what these groundbreaking technologies are, but why they matter to your future, their immense potential, and, well, the profound challenges that stand in their way.
Right.
We're going to be looking at every angle, from pathways for aggressive emissions reduction, vital adaptation strategies, to even the more controversial stuff like large-scale atmospheric intervention.
And what's really striking here isn't just the anecdotal evidence we see all around us, but the rock-solid scientific consensus behind it. The Intergovernmental Panel on Climate Change, the IPCC.
A big one.
Exactly. The leading international body for assessing climate science. In its sixth assessment report, the AR6, it states unequivocally, human influence has warmed the planet, leading to widespread, rapid, and intensifying changes.
Unequivocally. That's the key word.
It really is. And beyond that startling 1.55 degree mark for 2024 you mentioned, just consider the greenhouse gas concentrations, CO2 levels, higher than any point in at least 2 million years.
2 million, wow!
Methane and nitrous oxide are at their highest in 800,000 years. And this isn't just about warmer air. It's driving an accelerating rate of global mean sea level rise faster since 1900 than over any preceding century in the last 3 millennia.
Yeah.
We are really, truly in uncharted territory.
So the science is crystal clear. It demands action. But what's been the global response? What's the policy framework actually designed to tackle this?
Well, in response to this escalating crisis, the international community came together back in 2015 with the Paris Agreement.
Right.
And this landmark treaty aims to limit global warming to well below 2 degrees C, and ideally pursue that more ambitious target of 1.5 degrees C above pre-industrial levels.
The 1.5 goal.
Exactly. And to achieve that critical 1.5 degree goal, the science is quite precise. Global emissions absolutely must peak before 2025.
Which is now, basically.
Pretty much yesterday, yeah. And then dramatically decline by 43% by 2030. That is an incredibly tight timeline. It demands immediate drastic shifts.
And that's where technology becomes absolutely central, doesn't it? It's not just about political will or policy shifts. It's about a complete technological transformation of our entire global economy.
You're absolutely right. Achieving these goals requires a technological shift of unprecedented scale, unprecedented speed, and frankly, ingenuity. The International Energy Agency, the IEA, estimates that roughly half of the cumulative emissions reductions we need by 2050 to reach net zero. Half. Will have to come from technologies that, right now, are only at the prototype or demonstration phase.
Still in the lab, basically.
Pretty much. And this is where this profound strategic tension emerges. We have these urgent near-term targets for 2030, yet many of the critical future technologies we'll need for deeper decarbonization have much longer development and deployment timelines.
Right, they won't be ready in time for 2030.
Exactly. We simply cannot rely solely on future innovations for the immediate drastic cuts required in the next, 6 years?
That's a fascinating and, frankly, a bit daunting tension. So how do we navigate this? Do we put all our chips on existing tech or bet big on the future? It sounds like we need, a dual strategy. What does that look like?
It's precisely a dual strategy, and it demands incredible coordination. First, an aggressive, almost emergency-level deployment of existing cost-competitive technologies.
Stuff we have now.
Think solar, wind, radical improvements in energy efficiency. These are our workhorses for hitting those drastic 2030 targets.
Okay.
But concurrently, at the same time, we need a concerted, deliberate effort to de-risk, demonstrate, and rapidly scale the next wave of innovations.
The future stuff.
The future stuff. These are the solutions we'll need for the deeper post-2030 decarbonization journey, the ones that will transform those industries that are currently really hard to abate. This isn't, a zero-sum game for funding or political will.
Yeah.
We have to walk and chew gum at the same time.
Right. Aggressively roll out solar while pouring billions into, say, untested next-gen solutions.
Exactly.
That perfectly sets the stage for our deep dive. Let's jump into that dual strategy then, starting with the very bedrock of any climate solution: decarbonizing our energy and industry. This energy system transition truly is the cornerstone, isn't it? Demanding a fundamental shift in how we generate, store, and ultimately consume power globally. Okay, let's unpack this first bit. When most people think of solar, they picture those familiar, often rigid, blue silicon panels we see everywhere. But what if there's a next-generation technology poised to, I don't know, completely rewrite the rulebook? Expert, tell us about perovskite solar cells, or PSCs. What makes them so special? Why are they being called a game changer?
Right, PSCs. They are genuinely compelling, and the potential is remarkable. Perovskites have this unique crystal structure that allows for remarkably high power conversion efficiencies. We're talking approaching 30% in lab settings.
30%? That's huge.
It is. That rivals and, in some cases, actually surpasses conventional silicon solar cells. But the real game changer, the profound implication you alluded to, is their potential for low-cost, low-energy manufacturing.
Ah, cheaper to make.
Potentially much cheaper, and using less energy to make them. Imagine solar cells not just on rooftops, but seamlessly integrated into flexible window films, maybe charging smart clothing or powering off-grid communities without the massive infrastructure needed for traditional silicon.
So much more versatile.
Exactly. I mean, solar could become even cheaper, more versatile, truly democratized, really, unlocking entirely new markets and applications.
That sounds incredible, almost, well, too good to be true. But if they're so good, why aren't they everywhere already? Replacing every silicon panel? There must be a catch, right?
You've hit on it. There's always a but, isn't there? The critical barrier right now is long-term instability. Perovskite materials are notoriously vulnerable to degradation from common environmental factors, things like moisture, oxygen, and especially heat.
So they break down easily.
They can, yeah. And recent research, particularly coming out in 2025, has focused intensely on understanding why. Scientists have identified this new and particularly tricky failure mechanism called photomechanical degradation.
Photomechanical? What's that?
Think of it like repeatedly flexing a piece of plastic or metal. Over time, that constant physical stress, the material actually expanding and contracting slightly under daily sunlight, creates tiny internal fractures and structural fatigue.
So it's not just a chemical reaction, it's physical wear and tear from the light itself.
Exactly. It's a physical stress, not just corrosion or chemical breakdown, that ultimately leads to performance decline and a shortened lifespan.
Oh, okay, that's a crucial distinction. Are scientists finding clever ways around this, or is it, a fundamental showstopper?
Oh, far from a showstopper. There's some really cutting-edge work happening. Researchers are exploring novel protective strategies. For instance, embedding tiny alumina, that's Al2O3 nanoparticles, within the perovskite structure.
Like reinforcing it?
Kinda, yeah, to create a more uniform protective barrier that dampens these physical stresses. Another promising avenue involves using graphene polymer composites for mechanical reinforcement, essentially making the cell tougher, more resilient.
Graphene, interesting.
Yeah. These approaches have shown significant promise in lab settings, extending operational lifespans by up to tenfold in some cases.
Tenfold, that's huge.
It is. Now, commercialization is still probably a few years out, but these advancements are critical steps towards making perovskites a truly viable, long-term energy solution.
That's a massive leap forward for solar. But okay, if we can harness the sun more efficiently, what about tapping into another immense, largely untouched source of renewable power? Expert, when we talk about harnessing wind, particularly in vast, deep ocean waters, floating offshore wind, FOW, is becoming a critical piece of the puzzle, isn't it?
Absolutely. Floating offshore wind is, well, essential for unlocking vast, deep water wind resources that are currently just beyond our reach.
Because the water's too deep for regular turbines.
Exactly. To put it in perspective, about 80% of the entire global offshore wind potential lies in waters deeper than 60 meters. Traditional fixed-bottom turbines, the ones bolted directly to the seabed, just aren't feasible there.
80%. Wow, it's huge.
Yeah.
As of 2023, the industry was still nascent, really just starting out. Only about 270 megawatts operational worldwide, barely a blip on the global energy map.
Tiny.
But the project pipeline is immense. A staggering 244 gigawatts are in various stages of planning and development.
Okay, that's a serious pipeline.
It signals robust market interest and the expectation that this technology will enter commercial gigawatt-scale deployment probably after 2026.
So it's about accessing wind resources that are currently out of reach, basically opening up a whole new frontier. What's the core innovation here? What makes them float? And are there big engineering challenges?
The core innovation really lies in the floating foundation designs themselves. These aren't just, scaled-up buoys. They are sophisticated marine engineering marvels.
Right.
We're talking clever solutions like semi-submersibles. Think of a giant, stable tripod floating on the surface. Those are critical for rough, deep waters like the North Sea, designed to handle massive waves.
Then you have spar buoys, which are these long, slender poles anchored deep below, incredibly stable, but they need very deep water to accommodate their long underwater part, making them ideal for calmer, deeper coastal shelf areas.
Different designs for different conditions.
Exactly. Other designs include barges, broad flat platforms, and tension leg platforms, or TLPs, which are held taut by cables to the seabed. Each is sort of a master of its domain, designed for specific ocean conditions.
Makes sense.
Now, while the levelized cost of electricity, the LCOE, basically the average lifetime cost per unit of electricity.
Right, the key cost metric.
Exactly. While that LCOE for offshore wind has dropped dramatically over the past decade, 2024 has unfortunately seen some headwinds. Inflation, supply chain disruptions, they've caused a slight temporary increase in costs.
Ah, okay. A blip, hopefully.
Hopefully, despite that powerful long-term downward trend.
Okay, getting the energy is one thing, but storing it efficiently is another huge piece, especially as we electrify more and more. When we think about the future of EVs, electric vehicles, or even grid-scale storage, there's one technology that keeps popping up as a real game changer: solid-state batteries. Expert, what's making everyone call this a paradigm shift? What makes them so transformative compared to the lithium-ion tech we have today?
Solid-state batteries, yeah, they truly represent a potential paradigm shift. The excitement is absolutely warranted. The key difference is fundamental. They replace that flammable liquid or gel electrolyte in conventional lithium-ion batteries with a solid material.
Solid instead of liquid, okay.
Right. Could be a sulfide, an oxide, a polymer, but it's solid. And this single change unlocks a whole suite of transformative improvements. You're looking at significantly higher energy densities, potentially exceeding 500 watt-hours per kilogram, YHKG.
500 kg, what does that mean in practical terms, like for an EV?
In practical terms, it could enable electric vehicles with ranges well over 500 miles on a single charge.
500 miles?
Yeah. Imagine driving from, say, New York to Cleveland without stopping to recharge.
That is truly enormous. That tackles range anxiety head-on. What else did they promise?
Well, beyond that incredible range, they promise dramatically faster charging times, potentially under 15 minutes.
Wow, like a gas station stop.
Pretty much on par, yeah. They also boast a much longer cycle life, projected maybe 15-20 years compared to the 5-8 years of current lithium-ion. So your car battery could actually outlast the car itself.
Longer lasting, too.
And crucially, superior safety. By eliminating that liquid electrolyte, they largely remove the risk of thermal runaway and fires that we sometimes associate with current EV batteries. Much safer for vehicles and grid storage.
Okay, higher density, faster charging, longer life, safer. That sounds like the holy grail for EVs. Given those incredible promises, what are the biggest hurdles? Why don't we have them in every EV already? Are major players actually investing in this?
Oh, they absolutely are. Major automakers like Toyota, Volkswagen, they're heavily invested. They're targeting commercialization in vehicles before 2030.
So, soon-ish.
Relatively soon, yeah. But the hurdles are substantial. The primary challenge is creating a stable, low-resistance, solid interface.
The connection between the solid parts.
Exactly. Between the electrodes and the solid electrolyte. Imagine trying to get two perfectly flat, rigid surfaces to stick together without any air gaps or imperfections at a microscopic level.
Tricky.
Very tricky. Now imagine doing that, ensuring electrons can flow freely across that boundary without resistance and maintaining that perfect contact and chemical stability over thousands of charging and discharging cycles. It's incredibly difficult.
Right. Making it last.
And on top of that, manufacturing processes for solid-state batteries are currently complex and expensive. So making them cost-competitive with established lithium-ion tech is a significant hurdle before mass adoption.
Okay, got it. Beyond batteries, we also need low-carbon fuels for those sectors that are notoriously hard to electrify directly, heavy industry, shipping, aviation. That brings us to green hydrogen. How exactly is it produced, and what role does it play?
Right. Green hydrogen. It's produced through the electrolysis of water, splitting water to hydrogen and oxygen, but crucially, it uses renewable electricity to power that process.
So zero-emission fuel.
Exactly. A truly zero-emission energy carrier, which makes it essential for those hard-to-electrify sectors you mentioned. The International Energy Agency's net zero scenario outlines a massive need, a staggering 560 gigawatts of electrolyzer capacity by 2030.
560 gigawatts. That sounds like a monumental task, building that much capacity so quickly. Are we on track for that, or is there a big gap?
Well, we have a substantial global project pipeline, nearly 520 gigawatts announced for 2030. So the ambition is definitely there.
Okay, the plans exist.
The plans exist. However, there's a critical investment gap. As of 2024, only a mere 4% of that announced capacity had actually reached a final investment decision, or FID.
Only 4%. Why so low?
The primary barrier, and it's a big one, is economic. Green hydrogen's production cost is currently maybe 1.5 to 6 times higher than hydrogen produced from fossil fuels without carbon capture.
The gray hydrogen.
Exactly. This green premium is a tough sell for industries operating on tight margins.
So how do we bridge that economic gap? How do we get green hydrogen down to cost parity? What needs to happen?
It really hinges on two main factors, and they're interconnected. First, continued and dramatic reductions in the cost of renewable electricity, which, as we discussed with perovskites and floating offshore wind, is actively being pursued.
Cheaper clean power.
Cheaper clean power means cheaper green hydrogen. Simple as that. Second, successful scaling of electrolyzer manufacturing to drive down their capital costs through economies of scale.
Making the machines cheaper.
Right. And crucially, supportive policies are playing a vital role here, stimulating these initial investments. We're seeing this with things like the production tax credits in the U.S. Inflation Reduction Act. They're designed to bridge this green premium in the early stages, create a market, and push down that cost curve.
Got it. Let's pivot now from fuel sources to transforming some of the world's most, well, stubbornly hard-to-abate industrial sectors. Steel and cement production are enormous emitters. What are the key pathways emerging for green steel?
Yeah, the steel industry alone accounts for about 8% of global CO2 emissions. Traditionally, this comes from using coking coal in blast furnaces to reduce iron ore.
The old way.
The old, very carbon-intensive way. The most developed and currently leading pathway for green steel is called hydrogen-based direct reduced iron, or H2DRI.
H2DRI. Okay.
This process basically replaces that coking coal with green hydrogen to reduce the iron ore. Then that reduced iron is melted in an electric arc furnace, an EAF, powered by renewables.
So hydrogen replaces coal and electricity replaces the blast furnace heat.
Essentially, yeah. It's a complete overhaul of the process. Most major steelmakers are heavily focusing here. There's nearly 100 million tons of hydrogen-ready capacity already announced by the mid-2030s.
That's significant. And beyond H2DRI, I read about a more revolutionary approach, molten oxide electrolysis. Sounds very different.
Molten oxide electrolysis, or MOE, yes. It's less mature, definitely, but potentially highly disruptive. It could be a real game changer if it scales. It's a direct single-step process.
Single step.
Yeah. It uses renewable electricity to directly split iron ore into liquid iron and pure oxygen. It completely bypasses fossil fuels and even the need for a green hydrogen supply chain.
Wow, no hydrogen needed, just electricity.
Just electricity and iron ore, basically. Imagine producing steel with essentially zero direct CO2 emissions in a single electrified step. Tech developers like Boston Metal are targeting commercialization by 2026.
That's soon.
That's the target. If successful, this would represent a quantum leap, potentially offering a more streamlined, ultra-low carbon steel production method.
Those sound like immense shifts for such a foundational industry. What are the main barriers to getting these deployed at scale, and what's actually enabling them, given the likely costs?
Immense capital costs are the primary barrier, no question. We're talking multi-billion-dollar investments to retool entire steel mills.
Huge investment.
Huge. What's enabling them, however, is this fascinating shift in market dynamics. Demand-side commitments.
Meaning
Major companies in sectors like automotive and construction, think Mercedes-Benz, BMW, GM, are proactively signing long-term offtake agreements for green steel, often years before it's even produced.
Oh, buying it in advance.
Exactly. This provides the revenue certainty producers need to secure financing for these massive projects. It de-risks the investment.
Smart.
And additionally, regulatory drivers, like the EU's Carbon Border Adjustment Mechanism, the CBAM.
The carbon border tax.
Right. That taxes carbon-intensive imports. It effectively creates a price signal that makes green steel more competitive by penalizing the high-carbon alternatives.
Okay, let's turn to green cement now. Another massive emitter, often flies under the radar compared to steel. What are the innovations here? Especially since, as I understand it, a lot of cement's emissions are inherent to the chemical process itself.
You're right, cement is a huge one and tricky. Traditional production emits about 0.66 tons of CO2 per ton of cement produced. And crucially, like you said, over half of that is from unavoidable process emissions, specifically the calcination of limestone. It's a chemical reaction, not just burning fuel.
So you can't just switch fuels?
Not entirely, no.
Yeah.
So it requires a genuinely multi-pronged approach. The most widely adopted and cost-effective method right now is clinker substitution.
Using less clinker.
Exactly. You reduce the amount of that emissions-intensive clinker by blending in alternative materials, things like fly ash from coal plants, granulated blast furnace slag from steelmaking, or calcined clays. This reduces both energy demand and those process emissions.
Okay, that helps. But beyond just blending, are there more fundamental changes in the works to truly decarbonize cement?
Absolutely. There's a strong push for alternative fuels and electrification. So replacing fossil fuels used to heat the cement kilns with things like biomass or green hydrogen, and powering other processes with renewable electricity. But even more transformative are novel cement chemistries that eliminate traditional clinker altogether.
Completely new recipes for cement.
Exactly. Companies like Hoffman Green Cement Technologies, Forterra, they're commercializing entirely new binder formulations. And what's really exciting is that some of these new cements can actually absorb CO2 during their curing process,
Absorbed CO2, so carbon negative.
potentially leading to ultra-low or even carbon-negative products, yeah.
Mm.
It's not just a tweak, it's a fundamental reimagining of what cement can be.
And given those unavoidable process emissions you mentioned earlier, I imagine carbon capture, utilization, and storage, CCUS, must play a significant role here too, maybe even indispensable.
Indeed. It's widely acknowledged that achieving near-zero emissions in cement will necessitate large-scale deployment of CCUS, because such a big chunk of emissions comes from that calcination chemistry itself, not just fuel combustion.
You have to catch it at the source.
You have to capture that CO2 at the source. This makes cement plants really prime candidates for point source capture technologies. And we're seeing several demonstration projects already underway globally, including in major producing nations like India, paving the way for wider adoption. And, if we connect this back to the bigger picture we touched on with steel, this green premium isn't just a cost barrier. It's actually creating this fascinating and really powerful new market dynamic. It's accelerating change.
How so?
Well, this premium, the cost difference for low-carbon materials like green steel and cement versus the traditional stuff,
Yeah.
what's driving companies to pay it is their focus on reducing their Scope 3 emissions.
Their supply chain emissions.
Exactly. All the indirect emissions in their value chain, suppliers, product use, everything beyond their own factory gates. They're increasingly willing to pay this premium, which, as we said with steel, provides that crucial revenue certainty for the pioneering green industrial plants.
So demand pulls the technology forward.
Precisely. It creates this virtuous cycle. The early adopters de-risk the technology, they absorb the initial higher costs, and they drive learning and economies of scale. That eventually reduces the premium for the broader market. It's a powerful, market-shaping force moving beyond just policy pushes. It's shifting from why would you pay more to why wouldn't you invest in a greener supply chain?
So, okay, bringing this section together, what does this all mean for the big picture of the energy transition? These technologies, next-gen solar, floating wind, solid-state batteries, green hydrogen, green steel, green cement, they're clearly impressive on their own, but how do they fit together systemically? Is there like a weakest link in this chain that could hold us back?
That's the crucial point. It's where, honestly, a lot of climate strategy can fall short. These technologies are not isolated solutions operating in a vacuum.
Right, they depend on each other.
Absolutely. Green hydrogen scalability is fundamentally constrained by the availability and cost of massive-scale renewable electricity. We need the solar and wind first. Similarly, the climate benefit of a huge EV fleet, even with amazing solid-state batteries, is only fully realized if that charging electricity comes from clean sources.
Otherwise, you're just shifting emissions.
You're just shifting emissions.
Yeah.
This creates a systemic challenge where progress is really dictated by the pace of the slowest moving component. And a critical bottleneck that comes up again and again in analyses, something we just can't ignore, is the inadequacy of our existing electricity grid infrastructure.
The grid
The
itself.
grid itself.
Yeah.
It simply isn't ready in most places to handle the massive influx of variable renewables like solar and wind and the huge surge in demand from widespread electrification of transport, heating, industry.
It wasn't built for that.
It absolutely wasn't. So without concurrent massive investment in grid modernization, in building out long-distance transmission, in smart grid technologies, breakthroughs in individual technologies like batteries or electrolyzers might just fail to translate into the systemic decarbonization we desperately need.
It's like building a superhighway for EVs, but having only, I don't know, dirt roads connecting the charging stations.
That's a perfect analogy. The connections, the infrastructure, are just as critical as the end-use technology.
Okay, this brings us to a crucial pivot in our discussion. As our remaining carbon budget diminishes, and let's face it, with a certain amount of climate change already locked in, we have to talk about approaches beyond just cutting emissions at the source.
Right, the reality of overshoot and existing impacts.
Exactly. These are the realms of, well, geoengineering and adaptation. They're necessary, perhaps even unavoidable now, but they represent really profound differences in approach, risk, and ethical implications. Let's start with carbon dioxide removal, or CDR, specifically the engineered solutions. First up, point source capture. How mature is that?
Point source capture, PSC, is relatively mature, yeah? It's well understood conceptually. It involves capturing CO2 from the concentrated flue gas of large industrial facilities, power plants, steel mills, cement factories, like we just discussed.
Filtering the smokestack, basically.
Pretty much, filtering pollution before it enters the atmosphere. As of 2022, there were over 190 facilities in various stages of development globally. And a 2025 report identified over 160 distinct technological solutions aiming to improve efficiency and reduce the significant energy penalty and cost that comes with it.
So it works, but it's costly and uses energy.
That's the core challenge, yeah. It's a well-established concept continually being refined for cost and efficiency.
Okay, that sounds like a solid foundation for industrial emissions. But what about direct air capture, DAC, pulling CO2 right out of the ambient air? That just seems like an infinitely harder challenge.
You're absolutely right. DAC is far more nascent and inherently challenging. CO2 is much, much more diffuse in the atmosphere, around 420 parts per million currently.
Tiny concentration.
Tiny compared to the concentrated streams in flue gas, which can be maybe 100 times higher or more. This dilution makes DTAC inherently far more energy intensive and therefore expensive.
Takes more energy to grab it.
A lot more. As of 2025, global DTAC capacity is minimal, capturing just over 10,000 tons per year.
10,000 tons? That sounds like nothing on a planetary scale.
It's roughly the annual emissions of maybe 2,000 passenger cars. It's tiny. However, the project pipeline is rapidly expanding. Several large-scale facilities are under construction, including a truly monumental 500 kiloton per year plant in the U.S., expected online in 2025.
Okay, 500 kilotons is a big jump from 10,000 tons. But still, compared to billions of tons of global emissions, what scale is truly needed for DTAC to make a dent?
It is indeed small in the grand scheme. The IEA's net zero scenario, that roadmap to limiting warming to 1.5 degrees C, calls for nearly 80 megatons of DTAC capacity by 2030.
80 million tons.
80 million tons, or, put it another way, 160 times the capacity of that single 500 kiloton plant we just mentioned. Achieving that scale represents a truly monumental technological, financial, and logistical challenge within the next few years. It really highlights the vast gap between current capacity and what's needed if DEA is to play a significant role.
Okay, and what about CO2 utilization, CO2U? Can we turn that captured CO2, whether from industry or the air, into something useful, something valuable?
CO2 utilization. Yeah, the idea is converting captured CO2 into valuable products. This could potentially create a revenue stream to help offset those significant capture costs.
Make money from CO2.
Potentially. Think synthetic fuels, polymers, chemicals, or even mineralizing CO2 into building materials like concrete. Imagine roads or buildings that actively store carbon.
Carbon storing concrete, interesting.
Right. However, there's a critical caveat here. The actual climate benefit depends entirely on two factors. First, the durability of the carbon storage in that final product.
How long does it stay locked up?
Exactly. Is it stored for decades, centuries, or just a few months before being released again? And second, the process requires the use of low-carbon energy, especially green hydrogen, in the conversion process itself.
Ah, the energy input matters.
Critically, if you use fossil fuels to power the conversion of captured CO2 into a new product, You essentially defeat the purpose. You could even end up with a net increase in emissions overall. The energy input for utilization must be clean.
Got it. Beyond these highly engineered solutions, we also have these novel CDR pathways that try to enhance natural carbon sinks, sort of playing on Earth's own processes. Let's talk about enhanced weathering. How does that work? What are the pros and cons?
Enhanced weathering, or EW, aims to accelerate Earth's natural NO2 removal process. There's this slow geological phenomenon called silicate weathering that removes CO2 over millions of years.
Speeding up geology.
Kind of, yeah. The idea is to mine, grind, and then spread vast quantities of specific silicate rocks like basalt or olivine onto agricultural lands or coastal zones. These finely ground rocks then react with atmospheric CO2 much more rapidly than they would naturally,
Knock it away.
sequestering it as stable bicarbonate ions in water or as carbonate minerals in the soil. It's essentially giving nature a chemical nudge to work faster.
That sounds intriguing. Are there co-benefits? Or are there significant hurdles beyond just the basic chemistry?
There are definite potential co-benefits, things like improving soil fertility by releasing nutrients or helping to counteract ocean acidification by adding alkalinity to water.
Okay, good side effects.
Potentially. However, it faces substantial hurdles. We're talking about the truly vast scale of mining and transport required to move billions of tons of rock globally.
Huge logistical operation.
Massive. Then there's the significant energy intensity of grinding these rocks down to a fine powder that takes a lot of energy. And potential ecological risks from releasing heavy metals like nickel, which are naturally present in some of these rock types, into the environment.
Environmental risks, too.
Yes. And critically, perhaps the biggest hurdle is the immense difficulty of measurement, reporting, and verification MRV.
Measuring if it actually worked.
Exactly. Reliably quantifying the net CO2 removal against the complex dynamic background of natural carbon fluxes in soils and water. It's an extremely challenging scientific and logistical puzzle. It's very hard to definitively prove, yes, X amount of CO2 was removed because of this action, and it will stay removed.
Hard to track. Okay. And then there's ocean iron fertilization. This one always sounds a bit sci-fi and, frankly, highly risky. What's the theory behind it, and has it actually been proven to work as a CDR strategy?
Ocean iron fertilization, OIF, yeah, it definitely has that sci-fi feel. It seeks to leverage the ocean's immense capacity for carbon storage. The theory is you add iron, which is a limiting nutrient in some vast ocean regions, to stimulate massive phytoplankton blooms.
Well, algae blooms.
Exactly. These tiny marine plants, phytoplankton, draw down huge amounts of atmospheric CO2 through photosynthesis. As they die and sink, a portion of that carbon would theoretically be sequestered deep in the ocean, far from the atmosphere.
Theoretically, does it work in practice?
Well, early experiments have confirmed that OIF can indeed induce phytoplankton blooms. You add iron, you get a bloom. But its effectiveness as a durable CDR strategy, meaning long-term, verifiable carbon sequestration, remains highly uncertain. A lot of that carbon might just get re-released relatively quickly as things decompose higher up in the water column.
So it creates a bloom, but maybe doesn't lock the carbon away effectively. What are the major concerns, particularly the ecological ones, that make this so controversial?
The major concerns are profound and wide-ranging. There's that fundamental question about the durability of the sequestered carbon, how much sinks, how deep, for how long. But even more pressing are the potential for severe, unpredictable ecological side effects.
Like what?
Things like creating anoxic zones or dead zones in the ocean where oxygen levels plummet and marine life suffocates. It could also alter marine food webs in completely unforeseen ways, and it could lead to something called nutrient robbing.
Nutrient robbing.
Yeah, where stimulating blooms in one area deprives downstream regions of essential nutrients, potentially harming fisheries and ecosystems that depend on those nutrients flowing naturally. The sheer complexity of ocean ecosystems means the risks are substantial and really not fully understood. It's a very high-stakes gamble with very uncertain outcomes.
Okay, this raises an important and maybe uncomfortable question. If we can't cut emissions fast enough, and even CDR is slow or risky or hard to measure, what about actively reflecting sunlight back to space? What exactly is solar radiation management, or SRM, and why is it so contentious?
Right, SRM. It's crucial to state up front, unequivocally, SRM does not address the root cause of climate change.
Doesn't fix the CO2 problem.
Not at all. It doesn't remove greenhouse gases. It is absolutely not a substitute for aggressive emissions reductions. Instead, SRM refers to this set of highly controversial, largely theoretical techniques that aim to cool the planet by reflecting a small percentage of incoming sunlight back to space.
Like putting a giant sunshade over the Earth.
That's a common analogy, yeah.
Hmm.
It would treat a symptom, the warming, not the disease, which is the GHG buildup.
The most prominent, the most discussed SRM proposal is stratospheric aerosol injection, SAI. How would that work? What are the proposed benefits, and crucially, what are the profound risks everyone talks about?
Stratospheric aerosol injection, SAI, would essentially mimic the cooling effect of large volcanic eruptions, which we've observed happen naturally.
Like Mount Pinatubo.
It's exactly like Pinatubo. It involves injecting reflective particles. Sulfur dioxide is the most commonly proposed one, into the stratosphere, way up high, using maybe a fleet of high-altitude aircraft or even balloons. Climate models suggest that SAI could be fast-acting,
How fast?
potentially halting global temperature rise within just a few years. And it could be relatively inexpensive to deploy compared to the multi-trillion-dollar cost of decarbonizing the entire global economy.
Fast and cheap. Sounds tempting. What's the downside?
The downsides are profound and potentially catastrophic. Models suggest severe disruption of regional weather patterns, like the vital Asian and African monsoons, which could lead to widespread drought or floods affecting billions of people.
Messing with monsoons. Wow.
It could also cause depletion of the stratospheric ozone layer, the layer that protects us from harmful UV radiation. And perhaps most terrifyingly, there's what's called termination shock.
Termination shock.
Yeah. Imagine deploying SAI for decades. If that deployment were ever abruptly stopped due to war, economic collapse, political disagreement, whatever, before greenhouse gas levels were sufficiently reduced, the planet would experience rapid, devastating warming. It would snap back to its natural warming trajectory, but at an incredibly accelerated pace. The consequences for ecosystems and human societies could be unimaginable.
That sounds absolutely terrifying, like pulling the rug out from under the entire planet's climate system. What about marine cloud brightening, MCB? Is that considered maybe a less risky alternative?
Marine cloud brightening, MCB, involves spraying fine sea salt aerosols into low-lying marine clouds, usually over the ocean. The idea is to increase the number of cloud droplets, making the clouds whiter and more reflective.
Making clouds brighter to reflect more sun.
Exactly. It's often perceived as more localized and potentially less risky than SAI, maybe focusing on specific oceanic regions to achieve cooling effects. However, research published as recently as 2025 indicates that even MCB, despite its seemingly localized nature, could have far-reaching and unintended consequences.
Even brightening clouds locally could have global effects.
Potentially, yes. Things like altering large-scale atmospheric circulation patterns or even impacting the ozone layer far above the intervention site. The complexity of Earth's interconnected climate system means that even seemingly localized interventions can have global ripples and cascade effects that are just very difficult to predict accurately with current models.
Given these global impacts, the profound risks, the sheer scale, what are the governance challenges for SRM? It just sounds like a geopolitical nightmare waiting to happen.
The governance challenges for SRM are perhaps even more daunting than the technical ones. We currently have no international treaty, no institution with the authority, the mandate, or even the agreed-upon scientific and ethical framework to govern SRM research, let alone deployment.
No rules.
No rules. And the potential for unilateral deployment by a single nation, or maybe a small coalition of nations, without global consensus. That could trigger unprecedented geopolitical conflict, because the impacts would be global, almost certainly unevenly distributed, creating distinct winners and losers with very little recourse.
A recipe for conflict.
Absolutely. Furthermore, the very existence of SRM as a potential fix creates a significant moral hazard.
The worry that it makes us lazy about cutting emissions.
Exactly. It potentially reduces the incentive for the difficult, expensive, but absolutely essential work of reducing greenhouse gas emissions by offering this seemingly cheaper, faster alternative. It distracts from tackling the root cause. This isn't just a technical challenge. It's a profound ethical and diplomatic one for all of humanity. And, this brings us back to a challenge we touched upon earlier with enhanced weathering, one that is absolutely critical for the credibility and scalability of many climate interventions, especially CDR, the measurement, reporting, and verification, the MRV conundrum.
Right, proving it works and the carbon stays gone.
Precisely. For these open system CDR technologies like enhanced weathering and ocean iron fertilization, MRV is not just a challenge, it's arguably the central and largely unresolved obstacle.
So, Why is MRV so much harder for these open systems, the ones that interact directly with natural processes, compared to, say, direct air capture, where you can literally measure the CO2 going in and out of the machine?
Well, for contained systems like DC, where you can directly meter the CO2 as it's captured and then, say, inject it into a geological formation for storage, MRV is relatively straightforward. You have a pretty good handle on what you've removed and stored.
You can count it?
You can count it, more or less. But for open system approaches like EW or OIF, reliably quantifying the net amount of anthropogenic CO2 removed from the atmosphere against this huge backdrop of large, complex, and highly variable natural carbon fluxes from soils, vegetation, oceans moving carbon around constantly. Yeah. It's an immense scientific and logistical challenge.
It's like trying to count individual raindrops in a hurricane.
That's a great analogy. Studies show that on short timescales, the actual carbon removal efficiency of enhanced weathering, for example, can be very low, and the very definition of when and where the carbon is considered permanently removed, and for how long is it, 100 years, 1,000 years, is often ambiguous.
So the accounting is really fuzzy.
Very fuzzy. And this MRV gap isn't a minor technicality. It is a fundamental barrier to finance and scalability. Without trusted, robust verification protocols, investors can't accurately price the risk, carbon credit markets lack credibility, and policymakers can't design effective incentives or regulations. So the true readiness of any open system CDR technology is as much about its MRV methodology as its capture mechanism. It's the critical missing piece of the puzzle for many of these approaches.
Okay, so mitigation and even geoengineering are about addressing the causes or the symptoms of climate change. But what about adapting to the changes that are already locked in? The impacts that are now sadly inevitable. That's where adaptation technologies come in, right? Shifting focus to building resilience.
Precisely. While our mitigation efforts are absolutely crucial and must be accelerated, a certain degree of climate change and its impacts is already baked in. It's inevitable, so societies must adapt. Adaptation and resilience technologies are therefore essential.
What's the goal there?
The goal is to help communities cope with the impacts, everything from water scarcity and food insecurity to rising sea levels and more extreme weather events. It's about learning to live with and hopefully thrive despite a changed climate.
Let's start with enhancing water and food security, which are just foundational to human well-being. What's new and promising in, say, atmospheric water generation, pulling water from the air?
Atmospheric water generation, AWG, yeah. It offers a decentralized and incredibly flexible potential solution to water scarcity, literally extracting potable water directly from atmospheric humidity.
How does it work?
There are two main methods: cooling condensation, which basically chills air below its dew point, like a dehumidifier, and wet desiccation, which uses absorbent materials to chemically draw water from the air.
Interesting. What are the trends?
In 2025, key trends include the seamless integration of solar power for off-grid operation, making them viable in remote areas without reliable electricity, and the use of IoT sensors to optimize efficiency based on real-time humidity and temperature.
Making them smarter.
Exactly. However, challenges remain: high capital costs for large-scale systems and inefficiency in regions with very low humidity. Unfortunately, that limits their application in some of the world's most arid and water-stressed areas. But for others, it could be a lifeline.
And desalination is another critical technology for freshwater, especially for coastal regions. What are the advancements there making it more sustainable? Because it's traditionally very energy hungry, right?
It is. Advanced desalination is indeed indispensable for many coastal regions facing severe water stress. Conventional reverse osmosis, RO, is effective, but famously energy intensive. And honestly, it's approaching its thermodynamic efficiency limits. We can't squeeze much more out of it.
So what's next?
The future lies in developing lower cost, more energy efficient next generation technologies. But here's where it gets truly innovative. An exciting frontier is integrating desalination with carbon removal processes.
Combining water and carbon capture? How?
Instead of just dumping the concentrated saltwater byproduct of desalination, the hypersaline brine back into the ocean, where it can harm local ecosystems.
Right, the salty waste.
Yeah. The idea is to use this brine as a resource. By processing it or strategically returning it to the ocean in specific ways, it can actually react with and capture atmospheric CO2, essentially increasing the ocean's natural ability to store carbon, what's called ocean alkalinity enhancement.
So you get fresh water and D, remove CO2.
Potentially, yeah.
Right.
Synergistic system. It's a true two birds, one stone approach to two critical global challenges.
That's a fascinating connection. What about making our food supply more resilient and efficient through precision agriculture?
Precision agriculture represents a real paradigm shift in farming, moving away from treating whole fields uniformly to a highly targeted, data-driven approach.
Farming smarter.
Much smarter. By leveraging technologies like high-accuracy GPS, remote sensing from satellites and drones, in-field IoT sensors measuring soil moisture and nutrients, and AI-powered analytics, farmers can precisely manage inputs.
Like water and fertilizer.
Exactly. Water, fertilizer, pesticides,
Mhm.
based on the specific needs of different zones within a field, sometimes down to the level of individual plants. This site-specific management can increase crop yields by up to 30% in some cases, while dramatically reducing resource waste.
More crop, less waste.
Right. And it's a powerful tool for both climate adaptation by increasing drought resilience and optimizing water use and climate mitigation, by optimizing nitrogen fertilizers, which are a major source of nitrous oxide, a potent greenhouse gas. It's about getting more from less, intelligently.
Beyond food and water, we desperately need to protect our communities from increasingly intense and frequent extreme weather. How are we building resilient infrastructure and improving early warning systems?
Climate-resilient infrastructure is about proactively designing new infrastructure and retrofitting existing assets, like transport networks, energy grids, buildings to withstand future climate hazards.
Building stronger stuff.
Stronger, but also smarter. It means going beyond traditional engineering to incorporate forward-looking climate projections into design standards and material selection. Key strategies include using advanced, more durable materials, elevating critical assets above projected flood levels, and crucially, integrating nature-based solutions.
Like what?
Like restoring coastal mangroves to act as natural buffers against storm surges, or planting urban green spaces and green roofs to mitigate open heat island effects and manage stormwater. Tools like the Coalition for Disaster Resilient Infrastructure's Global Infrastructure Risk Model (GRI) are helping decision-makers assess risk and prioritize these investments effectively.
And with more intense events, timely warnings are absolutely crucial. How are AI-powered early warning systems evolving? And importantly, are they reaching everyone who needs them?
AI-powered early warning systems, EWS, are truly transforming disaster risk reduction. By applying sophisticated AI and machine learning algorithms to these vast streams of data from satellites, weather models, ground sensors, these systems can provide faster, more accurate, and far more localized forecasts for impending disasters.
Pinpointing the threat better.
Exactly. Hurricanes, floods, wildfires. This allows for more effective emergency response, saving countless lives and significantly reducing economic damage. However, in this big however, the UN's Early Warnings for All initiative highlights a critical, frankly disheartening gap.
What's the gap?
As of 2025, half of the world's population is still not covered by an adequate early warning system.
Half the world. Wow.
Yeah. And the primary challenge isn't just generating the warning, it's ensuring it reaches the last mile. Getting it to vulnerable communities, often in remote areas, and making sure it translates into effective, life-saving action on the ground. The tech is only part of the solution. And, what's truly fascinating here, and maybe a bit concerning, is how many of these adaptation technologies, precision ag, AI warnings, reveal this deeper systemic vulnerability, the digital divide.
Access to technology.
Precisely. The efficacy of systems like precision agriculture, which depends heavily on GPS, IoT, reliable internet, data analytics, and AI-powered early warning systems, which rely on robust connectivity to get data in and warnings out. It's fundamentally limited by access to reliable digital infrastructure and the digital literacy needed to use these tools effectively.
So if you're not connected, you miss out.
You miss out, potentially catastrophically. This creates a significant risk of a two-tiered adaptation landscape. Technologically advanced, well-connected regions will enhance their resilience, using these tools to protect their communities and economies. Meanwhile, digitally excluded communities, often the most vulnerable to climate impacts in the first place, lacking basic internet or smartphone access, are left further behind, unable to benefit.
Widening the gap.
Exactly. This disparity transforms adaptation from a purely technical challenge into a profound matter of digital justice. For adaptation policies to be truly effective and equitable, they absolutely must treat digital infrastructure not as some luxury add-on, but as an essential component of climate resilience itself. It's an urgent investment in human security.
It's clear, expert, we have this incredible array of technological solutions and innovations emerging from labs and pilot projects across all these areas. But transitioning from a lab-scale prototype or even a single large plant to a truly planetary-scale solution that involves this complex web of challenges that go far beyond just the pure technology itself. What are these big, overarching hurdles we face?
That's precisely the point where the rubber really meets the road. We can look at this through the lens of technology readiness levels, TRLs, that scale from 1 to 9 for estimated maturity.
Right, from basic idea to proven system.
Exactly. Achieving a high TRL, maybe 7, 8, 9, a proven prototype that works in a relevant environment is necessary, but often woefully insufficient for large-scale climate impact. The real hurdle is scalability.
Going big.
Going truly global. We need to build robust, ethical supply chains for critical minerals, lithium, cobalt, rare earths, which are often concentrated geographically and geopolitically sensitive. We need unprecedented manufacturing capacity for things like electrolyzers, solar panels, batteries, factories on a scale we've barely imagined.
Building the factories to build the tech.
Right. And critically, we need vast, new, enabling infrastructure. Think electricity transmission lines spanning continents, CO2 pipelines stretching thousands of kilometers, massive hydrogen storage facilities underground.
The whole support system.
The whole support system. There's also a fundamental physical constraint here. There's no Moore's law for capturing gigatons of CO2 or deploying terawatts of renewables. We can't just make a chip smaller and faster. We're dealing with the basic physical limits of material flows, energy requirements, land use, needed to move molecules and manage energy at planetary scale.
That makes perfect sense. So even if the tech works flawlessly, getting it to the scale we need is this massive undertaking involving far more than just brilliant engineering. What about the economics? Money always seems to be a major factor, especially for these huge capital-intensive projects.
Absolutely. Money makes the world go round, and the energy transition is no exception. While mature renewables like solar and wind are now often cost competitive, sometimes even cheaper than building new fossil fuel generation, many emerging climate solutions still face that significant green premium we talked about.
The extra cost for being green.
Right. This premium reflects higher capital costs for first-of-a-kind plants, nascent supply chains that haven't yet achieved economies of scale, and the inherent technology risks associated with new ventures. Investors see risk.
So what are the key financial barriers?
High upfront investment needed for these capital-intensive projects is a big one. Difficulty securing affordable financing, especially in emerging markets and developing economies, where the perceived technology and policy risks are often higher. And insufficient de-risking frameworks, ways to blend public and private finance effectively to lower the risk for private investors. Globally, the climate finance gap remains immense. Tracked investment is falling far short of the trillions needed annually to truly decarbonize the global economy. And this raises that really important question again, for all these technologies struggling with that green premium. How do we make these new vital technologies economically viable? How do we make them attractive to investors, not just, altruistic pioneers?
Yeah, how do we make the numbers work?
Well, carbon pricing through mechanisms like emissions trading systems, ETS, or carbon taxes is widely recognized by economists as arguably the most efficient and powerful policy instrument here.
Putting a price on pollution.
Exactly. The true insight of carbon pricing is its elegant simplicity, really. By putting a visible market-based cost on CO2 pollution, it internalizes that environmental damage into every economic decision companies and individuals make.
Makes pollution expensive.
It does. But it's not just about taxing, it's about re-engineering market signals so that innovation in clean solutions becomes the most profitable path, not just the right thing to do ethically. It helps close that green premium by making the dirty options more expensive, thus driving private investment and innovation towards low-carbon technologies.
And the revenue.
That's an added benefit. The revenues generated from carbon pricing can be recycled, used to fund the transition itself, support affected communities through the change, or even reduce other taxes like income tax, potentially making it more politically palatable.
It seems to me, expert, listening to all this, that the biggest barriers aren't always about the tech itself anymore, but about us, humans. When we talk about the human dimension of this transition, what exactly are those policy, governance, and social challenges that stand in the way of deploying all these brilliant solutions we've discussed?
You've hit on an absolutely critical point. The deployment of climate technologies is fundamentally a human endeavor, and it's constrained by human systems. Policy and regulatory hurdles are among the most frequently cited barriers globally.
Like what specifically?
We see unstable or unpredictable policy environments that just deter the kind of long-term, multi-billion-dollar investments needed, especially when project timelines span decades. Who wants to invest if the rules might change next year?
Right. Uncertainty kills investment.
Absolutely. Then there are cumbersome and notoriously slow permitting processes for essential infrastructure, renewable energy projects, transmission lines. Getting approval can take years, sometimes a decade or more.
The infamous red tape.
Exactly. And critically, for entirely new industries like green hydrogen or carbon capture, there's often an absence of clear, harmonized technical standards and regulations, which creates uncertainty for developers and investors alike. How do you build something if you don't know what rules it has to meet?
And what about public acceptance? That social license to operate. That can make or break a project regardless of how good the tech is.
Right. Absolutely critical. Public opposition to large infrastructure projects, whether it's a wind farm spoiling a view, a high-voltage transmission line crossing farmland, or a CO2 pipeline running near communities, can cause significant delays or even outright cancellations. We see it all the time.
NIMBYism, not in my backyard.
That's part of it, but it's often more complex. Policies perceived as unfair, policies that impose visible costs on households like higher energy bills or fuel taxes without clear, tangible benefits, or policies that fail to distribute the impacts of the transition equitably. They're likely to face strong political resistance and public backlash.
Which underscores the need for
The absolute necessity of a just transition. This is a framework, a guiding principle, that ensures the shift to a low-carbon economy is fair and inclusive. It means providing robust support for workers and communities currently dependent on fossil fuel industries, ensuring they have pathways to new livelihoods. And it means ensuring that the benefits of the green economy, clean air, new jobs, lower energy costs, eventually are shared broadly across society, not just concentrated among a select few. Without this focus on justice and fairness, technological solutions will inevitably flounder in the face of human resistance and political opposition.
This also brings us back to those really deep ethical dilemmas, especially with something as potentially world-altering and untested as geoengineering. How do we even begin to navigate those conversations?
Indeed. Emerging technologies, particularly geoengineering like SRM, introduce these profound ethical dilemmas that demand broad societal deliberation, not just closed-door scientific assessments. The questions surrounding unintended consequences are enormous.
Yeah.
What if we deploy a global sunshade and it inadvertently causes drought in a vital agricultural region halfway across the world? Who is responsible?
Huge questions.
Then there's the concept of intergenerational equity. Are we simply kicking the can down the road, passing on a bigger, more complex problem to future generations by relying on a techno-fix instead of addressing the root cause of emissions now?
Right.
There's the potential for weaponization. Could climate modification technologies ever be used coercively by one nation against another? A terrifying thought.
Right.
And of course, that ever-present moral hazard we discussed. Does the mere possibility of a technological fix reduce our collective urgency and incentive for the difficult but absolutely essential work of cutting emissions at the source?
Big, big ethical minefield.
It really is. We desperately need robust global governance frameworks to grapple with these issues, frameworks which, as we noted, currently do not exist. These aren't just academic debates, they are fundamental questions about humanity's role in shaping the planet and our responsibility to each other now and in the future. And, if we try to connect all these challenges, the technical scaling, the economics, the policy, the social acceptance, the ethics, it really boils down to this fundamental trilemma. The deployment of climate technologies is ultimately governed by this trilemma.
A trilemma. Okay, tell us more about that. What are the three elements and how do they interact? Why is it such a central challenge?
The trilemma involves three competing and often conflicting imperatives. First, there's speed. The scientific reality of climate change demands unprecedented speed in the transition to meet those critical near-term emissions targets, like the 2030 deadline we keep mentioning. We have to move fast.
Okay, speed. What's number two?
Number two is cost. Economic and political realities demand that this transition be achieved at the lowest possible cost to maintain economic competitiveness, avoid disruption, and secure broad public support. People worry about the cost.
Speed, cost, and the third.
The third is justice. Social and ethical sustainability demands a just transition, one that is inclusive and equitable, ensuring that the burdens and benefits are fairly distributed across society and globally. We talked about the importance of fairness.
Speed, cost, justice, and they conflict.
They often do. Navigating this trilemma is the central, agonizing task of climate policy. An overemphasis on speed, for example, might lead to cutting corners on community consultation or environmental safeguards, triggering backlash that ultimately stalls progress.
Rushing causes problems.
Right. A singular focus on cost might favor the cheapest solutions today, even if they perpetuate existing inequalities, deepen the digital divide, or lock in suboptimal technologies for the long term.
Cheap isn't always best.
And conversely, a process that prioritizes absolute justice above all else, while noble, might become so complex and slow that it fails to meet the urgent deadlines imposed by the physics of the climate system.
That's a balancing act.
It's a constant, delicate negotiation. A successful strategy is not one that tries to maximize any single objective speed, cost, or justice, but one that finds a politically durable and socially acceptable balance among all three.
We've taken a truly extensive journey today, haven't we? Through this expansive, dynamic landscape of future climate technologies. From next-gen renewables like perovskite solar and floating offshore wind to those revolutionary shifts needed for green industry and steel and cement. We've explored the, frankly, high-stakes world of carbon dioxide removal and even solar radiation management, and looked at the indispensable role of critical adaptation strategies for water, food, infrastructure, resilience.
And I think a central, really undeniable finding from this deep dive is crystal clear. There is no single silver bullet technology for the climate crisis. It just doesn't exist.
No magic wand.
No magic wand. The sheer scale, the complexity, the interconnectedness of the challenge necessitates a multifaceted, portfolio-based approach. We need a combination of diverse solutions, and these will vary by region, they'll need to be tailored to local context, and they'll undoubtedly evolve over time as new innovations emerge. And perhaps the most critical conclusion, the real bottom line. The primary barriers to effectively addressing the climate crisis are, arguably, no longer purely technological. For nearly every major emission source, a technical solution either exists already or is in a late stage of development.
You basically know how to do a lot of this stuff.
We do, technically speaking. The most significant hurdles lie squarely in those interconnected realms of economics, policy, and social systems. The transition is constrained by the green premium for nascent technologies, by vast investment gaps that require creative financing solutions, by the inertia of incumbent industries and interests, by cumbersome regulations, and by that profound challenge of securing genuine public acceptance and social license for the massive changes required. It is, fundamentally, a complex technosocial systems challenge.
Technosocial, I like that framing.
So the path forward really requires an integrated, four-pronged strategy that embraces this technosocial reality. First, rapidly deploying the mature, cost-effective technologies we already have with urgency.
Go, go, go with solar and wind.
Exactly. Second, aggressively de-risking and accelerating the emerging innovations we'll need for the next phase.
Helping the new tech get cheaper and proven.
Right. Third, responsibly governing the high-risk technologies like SRM through serious international dialogue and robust ethical frameworks. We need rules before anyone even thinks about deployment.
Handling the risky stuff carefully.
Very carefully. And fourth, crucially, embedding the principles of a just transition into every single facet of climate policy, building that broad social consensus and ensuring no one is left behind in this monumental shift.
Deploy, de-risk, govern, embed justice. Okay. As you, our listener, consider this deep dive, think about this. If we already have many of the technical solutions to prevent catastrophic warming, and the biggest hurdles are, as we've discussed, our financial systems, our political will, our ability to cooperate across borders and communities, what is the single most impactful lever you believe we could pull right now to accelerate this global transformation? What would truly unlock our collective potential to make this happen?